Let's take a look at the Collections API. This chapter, we're looking at the way the Collections API works, at what are the Collection API interfaces and implementation classes, and some most obviously frequently used types of collections, such as lists, sets, decks, maps, etc. How to iterate through the collection content, some automation classes like collection class and its functionalities, and also we discuss what are the important concerns regarding concurrent access to collections. We'll actually have a later lesson that covers concurrency API in more detail, but in this particular lesson, at the very end, we're just talking about the effect of concurrency on collections as such, just specifically regarding collections. Anyway, well, let's start with the overview of what the Collection API is all about. Now, we've looked at how we can handle a number of values wrapped up in the array. Well, Collection API provides much more flexible automation, if you like, for the similar type of task that we could use array for. So how to create a collection of different values and manage it. I would not say that collection is actually physically using arrays inside. That may or may not be the case, and it depends on the type of the collection. But think about it this way. With arrays, you are confined to the array, which is indexed by an integer and is of a certain type, right? But then generally, if you think about it, imagine you wrap up the array into some kind of class. Well, in that case, that class can produce you various automations. And whatever it physically stores values inside as actually an array or not is kind of irrelevant. The point is you've got the behaviors that this outer class provides to manage a number of items that you want it to manage. So for example, classes could use generics. You can specify a type of what you want to store in a certain collection. Whilst arrays actually don't use generics. Array is a collection of elements of a specific type. So array per se is not using generics. Arrays are not dynamically expandable. Well, you could use system array copy or arrays copy off, but as such, the array itself is not expandable. You just have to programmatically create another array and then copy content from one array to another. But the collection classes, they can do these things. They enable generics, they allow to dynamically expand collection as appropriate. They allow you to provide alternative search and index capabilities. Arrays are always using an int index. But then if you think about a collection class, well, it doesn't have to use an int index. It could be more flexible than that. You could perform some validations of elements as you add them to collections. For example, check uniqueness. You don't allow, you may decide not to allow duplicates to be stored in certain collections. Order elements in a particular order, provide different operations that manage concurrency and thread safety, and provide mechanisms to conveniently iterate through the collection. Now, the Collection API defines a number of interfaces in the Collection API, a number of interfaces where each interface describes certain aspect or certain capability of collections. And then these interfaces are implemented with different implementation classes, also part of the Collection API. And what you need to understand first is what are these capabilities? What are the features? So first you look at the interfaces. And then once you understand what these capabilities are, then you look at which specific implementation class would you like to pick and use on which occasion to implement the behaviors that you require from that or the other collection. Okay, well, let's start looking at the Collections API. What are these interfaces and what are, well, at least some examples of collection implementation classes? The interfaces and the implementation classes of a Collection API allocated in the Java util package. And the topmost interface for Collection API is this interface called Iterable. So it provides a very basic generic features for all collections. For example, an ability to use collections to iterate through the contents of collection using for each loop. So that basically means that because all other interfaces and eventual implementation classes of the collection API descend from that interface iterable, it's like the ultimate parent for them all, right? It means that all collections can be used in for each loops that way, right? Which is great. Now, there's also an interface called collection, which is an extension of iterable, but that is adding extra capabilities to just iteration capabilities, but also adding capabilities such as adding and removing elements. So define how you do that. An interface list describes a collection where elements are indexed by an int. So it's kind of very similar to what you get from the array. In fact, the most commonly used implementation class that implements list interface is a class called Arraylist, which is kind of self-explanatory because it feels like an array from the perspective of an integer index behavior. Set is another interface in the Collections API, which performs a validation of what you add to the set, and it does not allow duplicates. So set checks that what you add to the set is a unique element, essentially. Yeah? Typical implementation classes for set, hash set, tree set, sorted set. Sorted set is actually a variant of the set interface, which is implemented by the tree set implementation class. Deck describes double-ended queue, yeah, which is a collection where you can add elements to top or bottom and remove elements from top or bottom. So with that, you can implement algorithms such as first in, first out, or last in, first out, something like that. Yeah, kind of imagine the deck as an, deck of cards, and you can draw cards from top of the deck or from the bottom of the deck, right? That's a typical example of the use of kind of comparison to what you can compare the behaviors of the deck. Then there is an interface called map. A typical implementation for that would be the class called hashMap. And that is basically a combination of a set of keys and a collection of values. You can think of a map as a table of two columns. That's what the map feels like, where the first column in that table is a set of unique values, quite similar to the idea of a key column in a table. And the second column in that map is type of collection, which is just representing any other values that you want to put into that map. Thus, each map entry is comprised of a unique key and a value. Right. So that's a high-level overview of the collection API, kind of the frequently used types of collections. Now, let's start with Arraylist. Right? So that's the most basic one. It's probably closest to the idea of the array. Well, kind of obvious from the name, isn't it? So Arraylist is a class that implements list interface. It has no arc constructor, which creates a list of 10 elements. However, if you start adding more elements to the list, it will just keep expanding. So you create an array list and you don't specify the size, how many elements, it will just keep expanding as you add in content. But by default, internally, it sort of pre-creates the storage for future elements to be placed into that array list of 10 items. You may specify specific size constructor with initial capacity. And again, it will grow beyond that size if necessary, automatically. You don't need to do any kind of, array copy. It will just do the growth itself. So you can specify a particular size. But I guess from performance point of view, it's a good practice to try to guess how many elements you'll eventually need and define the size that way. And you could also, and it's a common feature for all collections, you can also initialize one collection using contents from another. So for example, imagine you previously created a set, well, hash set, yeah? Created a set and you added some stuff to that set, and then you use that set to populate the list. And frankly, that works the other way around as well. So if in one part of a program, you feel like you want to use a collection with certain properties, certain behaviors, you choose to use list, and then another part of the program, exact same values, you want to use them in a collection of a different nature, of a different type of behavior, and you feel like, oh, there, I want to use set. Nice and easy, you can convert one into the other by just passing the other collection to the constructor of, well, the other collection, right? So these are the ways of creating array lists. There's also a method called asList. It's a factory method. And the method asList is a method of arrays class, yeah, asList. It creates a list of a fixed size, which is very much like an actual array, yeah? So fixed size, you cannot resize it. And it accepts an array as an argument or a var_arg. It's a comma-separated list of parameters. It works as well. Yeah, it works both ways. You can also create read-only instance of list by using a method of list_of that creates an immutable list, right? So you cannot modify anything in it. And as I've mentioned, the list expands as necessary. A small caveat, when I was saying you can't modify anything in the list, well, you cannot remove elements from read-only list or add elements to read-only list. But if objects you're storing inside the read-only list are themselves mutable, then you could still modify these objects. You wouldn't be able to add or remove them from the list because list is read-only. But if the object stored in the list has setSomething method, well, you can still call the setSomething method. So contents of the collection and its immutability has nothing to do with the mutability of collection itself. Yeah, collection might be mutable, but things stored inside it might not necessarily be mutable. It depends what you want to put into that collection. Okay, so that's a list object. Now let's take a look what are the typical operations you perform on the list. So there is this example, and I would like to kind of zoom into it and explain exactly what these operations are doing. But first, very briefly, we have operations that allow us to add values, update values, delete values, check existence of values, or search for values. Now let's take just a quick look at the details of that algorithm that we have here. So first, we create a couple of products, food and drink, right? And we then create, well, yeah, obviously they're allocated in memory, and then we're creating a list. Now, here's some interesting points that I would like to make. First of all, you may specify the initial capacity, but that's up to you. Remember, the list grows beyond the initial capacity if necessary. Second, you may constrain the list to use specific type using generics. So you're saying that's list of products. It will allow you to store subtypes of the product into the list, like food or drink. Yeah, they could go into that list. That's perfectly fine. However, did you notice that on the left-hand side, I'm using an interface rather than the actual implementation class as the type? So it's perfectly valid assignment. You can create a variable type of interface and assign to it any object a reference that actually implements that interface. That works. But why am I not actually using Arraylist on the left-hand side? Why is that? Well, I can, but maybe I'll change my mind about the exact type of list I would like to use, because the Arraylist is not the only class that implements the list. There are some intricate variances, and you may wish to use Arraylist on one occasion and maybe some other implementation on another occasion. We'll actually see later in this lesson what are the other, variants. Yeah, but polymorphism, it means that any general behaviors that lists describes, so list interface describes how they all work, and then you could assign just different implementation to that list variable and get a different implementation of these behaviors. But the way you declare the variable, you don't really need to know which particular implementation of the list you're decided to use on that or the other occasion. So it's actually considered to be a good practice to use an interface as your variable type rather than a specific class. Anyhow, so we created here a list, and we're saying that its capacity is to store just a couple of products. So that allocates another object in memory, right, which is that list itself. Internally, you think of a list as something indexed by an integer. Yeah, that's the nature of Arraylist. And in this particular case, because we use generics, we restrict the content storage in that list to just products. So on this occasion, we're saying this list will store just products. It's basically not yet initialized in terms of its content. So elements within that array list are null. Now, let's remember how arrays were created and initialized. When you created and initialized the array, you could have an array of primitives or array of objects. Well, you see, with Java Collections API, the collections are always of objects. There's no such thing really as a collection of primitives. So there's always object references, and by default, they're always null. What if I want to store like a bunch of integers here? Yeah, can I do that? Well, I'll have to use the wrapper class, you see. Instead of a list of products, I'll say a list of integer, not int, yeah, but integer. And then, yeah, sure, I could store the numbers there if I like, yeah, why not? But I can't use a primitive itself. That's just not allowed because primitives don't really function with generics, yeah. Generics is an object-oriented feature. It's not really the way the primitives work, because primitives are just simple values in a stack. They're not really references to objects. Anyway, so we have this pair of products, and then we have an array list with 2 slots reserved for, well, referencing these products. Let's add products to the list. Add one, add the other, and what will happen is instead of nulls, we now have actual references stored inside that array list that refer to the food and drink objects that are stored somewhere in a heap. So list is stored somewhere in a heap, cake and tea is stored somewhere else in a heap, and then the elements within that list are referring to these objects. So they're not null anymore. We just added some content there. Now, what is going to happen if I will use add method with a designated position? Apparently, I can do that as well. So if I say add something to position 2, well, I could add actually anything I like, including null, funny enough. That will expand the list for me. It will just add extra positions. And as for the position 3, that will also add a reference, and apparently will refer to P1. P1 is the cake, isn't it? Yeah. So sure, the uniqueness is not checked by the list. You can add the same object to the list twice if you feel like it. And as you can see, you can add null to the list again if you feel like it. Right, now what's going to happen if I will use the method add and I qualify the position, right? And then I add something here. So that position 2 was null and I just added something to position. Actually, that will push things forward. This is what's going to happen. So if I add a position that is in between existing positions, it pushes the rest of the list forward. So the elements will be, the element of position 2 will be inserted to reference, well, in this particular case, it's also referenced in the cake, and previous elements 2 and 3 became elements 3 and 4. Yeah, so they were kind of pushed forward here. So that's the add onto the position, which is not at the end, but in the middle. That's the behavior. You can also use the method set, and set allows you to actually update the value on a given position. So position 2, right, you're changing that from pointing reference in P1 to reference in P2 instead. Yeah, you performed essentially the update of the value. That's what set does. Now, can I maybe remove things? Sure. And there are 2 ways in which you can do it. You can remove elements using an index. So that will remove element from position 0, or actually you can remove an element by saying which element that is. So if you're saying remove element P2, what will happen is that the algorithm will search for the first occurrence of the element in here that refers to the P2 object. Apparently there are a couple of elements that are referring to P2, yeah? So we'll remove the first occurrence. So the element at position 0 and element at position 1, these two positions will be gone because I asked them to be removed, and the rest of this content will sort of be shifted forward and re-indexed for you. Yeah? So first two positions are gone, the remaining three positions shifted forward, and obviously index is adjusted. So the list always presents continuous index, basically, starting at 0. Okay, and what's going to happen if we will search and look for something within that list? So there's a contains method, yeah? And it tells you simply true or false. Do we have something that you're looking for, like P2 in that list? Or maybe we don't. You can also identify at which index the element is present. So that looks for first occurrence of a certain element. So in this particular case, that P1, where is that? P1 is cake, isn't it? So that will be position 2. That's the first occurrence of P1 element in that list. So that index will be equal to 2. And then lastly, yeah, so we located that. Yeah, that's the one we just looked for. And lastly, we could get elements on a given index. So that will get us this element at position 2. And actually, you can just invoke methods upon the object stored in that collection straight ahead. You don't need to extract them into some kind of intermediate variable. No, you just call a method, like set name, and it changes the name for the product from cake to cookie. Yeah, updated that. There you go. Lastly, what's going to happen if I will try to add an element at position 4? You obviously see that last valid position is 2, and we've seen before that you can add to position which is +1 to the last position. We did it earlier with these lines of code, add at position 2, add at position 3. That was fine, yeah, we could do that. But what if we try to jump the position? Well, that's not going to work. List will insist on actually presenting continuous collection without kind of gaps. Yeah, I mean, you could certainly insert null at a given position. That's fine, that's allowed, but you cannot just jump the position without defining anything at all. Yeah, so that will be an exception that will be thrown. If you try to do that, you would not be allowed to do it. Okay, so we've seen the evolution of this array list content, all of these manipulations. Now let's proceed to a set. And in this particular case, we're using an example of the set interface implemented by the hash set class. As you can see, there's certain things are very similar to the way the list works. For example, you can initialize the hash set by using previously initialized list by passing it to the constructor. Yeah, but you could create a hash set with no parameters at all that creates a hash set of 16 elements. You can also specify particular capacity, like hash set of 20 elements, but remember it expands if necessary, so it will just grow, yeah? And there's also this ability to set up the load factor. The default load factor is not 75, but you can change it to a different load factor. Why do we need the load factor, what it is, and why do you care, right? Well, you see, the hash set checks, like any other set, checks the uniqueness of what you're actually adding to the set. So you cannot add the same element to the set hash set twice. That's not allowed. Now, there is an implication here. In order to check the uniqueness, you have to basically look at the elements that are already in that set, right? Well, in a small size set, that's not a problem. But as the hash set will grow and you will start adding more and more elements to it, to check the uniqueness, to check that a new element you're adding does not overlap with anything that is in that set already, you would have to deal with larger and larger set of elements. And eventually your performance will start to degrade. So it will degrade with the growth of the set. which is not good. So can we improve that? And apparently HashSat has a built-in algorithm which is actually trying to improve that. And the algorithm is based on the idea that every element that is based in a set, that's placed in a set is added to a kind of a bucket of elements, to a segment of elements. And the set is subdivided into multiple such segments, into multiple buckets. And the elements are grouped into these buckets based on their hash codes. So all elements, all objects that are added to the set with certain similar hash codes are in one bucket, then another group of objects with different hash codes is in a different bucket. And that means when the hash set accepts an element that you're trying to add to it, it only needs to get its hash code, and it only needs to check one of the buckets, the one which is in range of that hash code value. It doesn't really need to scroll through the entire hash set to validate if this element occurs or not. It's enough for it to just check subset. So it's much quicker, obviously, and it's more scalable approach. But then for performance reasons, to redistribute the contents, as you start adding more and more elements, there is this idea of a load factor. If a subset, if the bucket within a set grows over a certain capacity, so you're adding, let's say, by default, more than 75% of entries are already added, then at that stage, the hash set will just create an additional bucket to accept more elements. So it will not fill every bucket to capacity. It will kind of leave space within every sort of internal group of object storages to accept extra objects that may fall into that range of hash codes that is the basis of grouping. It's an automatic process. It's not like you have to code any of that. HashSat already has the relevant algorithms, but it's just for you to appreciate what exactly it's trying to do and why there is this load factor parameter. Yeah, so you can basically specify how full you want internal storage within a set to get before the set starts reshuffling the buckets and optimizing that storage. So say, for example, default is 75%, and I'm saying actually I allow it to be up to the 85% full instead, right? Okay, so these are the ways of creating hash sets. One more note, set off, yeah, which creates a read-only set. Very similar to the list of, which remember created read-only list. Now, let's take a look at the operations we perform on a set. Yeah, so operations allow us to insert, delete elements, check existence. Again, let's just zoom in and play around with this example a little bit. So we first, we act upon the same premise that we have few objects which we allocate into memory, food, drink, and another food. Yeah, the three products basically. Yeah, so cake, tea, and cookie. Lovely. Now we create the actual hash set. And again, you could specify the size, but default is 16 elements. And we're saying that we're using generics. We'll accept any products to be added to that set. And just like with the list, we probably would like to use the interface name here. So maybe we change our mind and instead of hash set, later on decide to use another type of set implementation, right? So we wouldn't have to recode anything because our code is done, coded to the interface type. Anyway, so we create that hash set. And by default, remember, it creates capacity, storage capacity for 16 elements. Well, I didn't specify the size, so default is 16. And I'm not drawing all the 16 elements. Yeah, whatever. You know that they're there. And their values are not yet added. Yeah, so I haven't actually added anything. Now let's start adding values. So add, just add. And that would add an element, and add another one, and that would add another element, and so on. Yeah, so just simply call the method add. Oh, well, that's interesting. We add in the same element twice. So what's going to happen in this case? Well, actually, nothing, except that this method add apparently returns you Boolean value. Boolean indicator of true or false, which indicates whether it actually added something or not. So if the add method returns you false, you know that it actually ignored whatever you just tried to do, right? And why would it ignore it? Because the element P2 is already present in that collection. So it's not going to put it again because that checks the uniqueness. And then the next thing we do, we add another element, P3, and this one will actually be added. Yeah, of course, because that's not yet present in that particular collection. Now, what about remove? Sure, we can do that. Remove a particular element. Yeah, and we'll search through and remove that element. Okay, and what else we could do? We could remove again. How strange that is. Well, again, it just returns you Boolean. If it has nothing to remove, then it won't remove anything, and it has something to remove, well, then you know what it just removed. So there's also a method contains, which you can invoke, and that basically tells you true or false whenever the certain element is or is not present in that set. So we've looked at the way we manipulate with the set content, right? Now let's take a look at the DAC. Array DAC is an implementation of DAC interface and allows us to create these double-ended kind of queue where we could add and remove things from top or bottom of the queue. Again, the way of creating array DACs, you can create an array DAC with no parameters that creates a DAC of 16 elements, or you can specify capacity, and it expands if required automatically, and you can populate array DAC using the contents of another collection, for example, using a list, right? Or set, or whatever you like. So, now, how do we manipulate with array DACs? Okay, there are several algorithms that are available here. And again, let's zoom in and take a look at exactly what these algorithms are supposed to do. Yeah, but basically they implement first in, first out, or last in, first out behaviors. But let's take a closer look. The example here, again, assumes we have a couple of products, a few products that we allocate. Yeah, cake, tea, cookie, whatever, just some products. And then we create DAC object, array DAC object to store these products. And again, it creates an array DAC of 16 elements. That's a default. I would not draw all the elements, but that's basically what it feels like. Now, let's take a look at what will happen if we just try to get something from the array DAC, and there's nothing in there. Well, if you just try to do the poll and get the element, then you'll just get null if there's nothing inside. Okay, so that's nothing particularly exciting here. What will happen if we try to add elements? There are two ways of adding things. You can offer element first, and that will add it to the head of that DAC, to the top of the DAC. So let's say we call the offer first and we put the cake there, right? Now we call offer first again. What's going to happen is that that cake will be moved to the next position. And on the first position, well, we added something else. We added tea, yeah? So we actually kind of shifted the contents of the DAC forward and we added something to the top. That's offer first method. Now, when you then try to get values, you can do the poll first method. Poll method gets the first element from the head of the DAC and actually removes it from the DAC. So that will be gone, and then the contents will shift forward, and the first element in the DAC would become, whichever element was previously second will become first. So that's poll first. You can grab the element from the DAC without actually removing it. That's the pick first method. That allows you to get the first element, but not physically remove it out. The poll will remove it. Now, the next thing you could do is offer last. That allows you to add things to the tail of the DAC. So let's say offer last, and that adds it to the last position just after the last valid element that was in the DAC, right? So offering the element there, and again, you can keep offering, and what will happen is that further elements will be added behind that last position. And guess what? There is the opposite of poll first. there is an ability to poll last, and that will remove the last element, return it to you, and remove the last element from the deck. Okay, and use also peek last, and that allows you to look at what the last element is without actually physically removing it as such. And lastly, if you try to offer a null element, you will fail at that. That is not allowed. You cannot offer first or last a null element. You actually have to specify what it is that you want to add. There you go. That's how the array deck works. Right, so with array decks, we can do first in, first out, or last in, first out algorithms, and just generally treat it as kind of a flexible way of adding and removing things from top or bottom of a deck. Next, hash map. Hash map is a combination of two collections. It's like a table of two columns, which stores the first column as your keys and second column as your values. So it's like key value pairs, basically. You can construct a hash map using NORC constructor, which creates a map of 16 elements, which expands if necessary. You can specify initial capacity. You can also specify another hash map and maybe, kind of grab items from one map and put them in another, potentially. And also you can have this method of, which creates a map of specified predefined entries. The entries could be specified as key, comma, value, next, comma, next key, comma, next value, or these key value pairs could be wrapped up into the object called map entry. So you can do it that way. It's up to you. Yeah, so there's a method of entries that allows you first to group key value pairs into entries before you add them to the map. There's a slight performance advantage of using of entries versus method of, but in small maps, that's not dramatic. Okay, so yeah, an of method creates a read-only map as well. That's important to point out. Now, how do we manipulate with maps? Okay, so we can put, remove, get elements, and sort of check existence of elements within the map. Again, let's zoom into this example and observe how it actually works. In this scenario, we're looking at a pair of products again, cake and tea, and then we're allocating a map, or hash map, and notice that this map is using two columns, essentially. One key column, which is type of product, and the second one is a value, which is the integer. And let's assume that we're storing something like products and their quantities, like the order. Yeah. So, for example, the products will be these cake and tea, and then we order them in some quantities. But it's important to understand that the key is actually a set, so that means it's unique, right? And well, the value is just a list, so you could add same quantity to different products if you like, but you cannot duplicate the product in the map. Anyway, so you've allocated this hash map. By default, it comes as a map of 16 entries because I didn't specify the size in the constructor, but it will expand as necessary. And well, there are no values in that map yet, so let's start adding something. And when we add values, we basically just say what it is that we want to add, product P1, P2, and the integer, well, in this case, yeah, a value of 2. Strictly speaking, I should draw here, instead of the actual number 2, I should draw the arrow from here pointing to another chunk of memory where the integer object is stored, because integer is not a primitive, it's a wrapper class, so it's stored in a heap, yeah? But just to sort of declutter the graphics, I'm just drawing here the number 2. So in fact, you need to realize it's a reference to the integer object, really, rather than a primitive. Yeah, because you cannot use primitives with collection API, as you have to use objects. Anyway, so we've added some entries into that map. What will happen if we'll just try to put a different value for an existing element? So this P1 already exists in a map, right? But now we put in 5 instead of 2. Well, that will act as an update statement. So that value of 2 will be replaced with a value of 5. put method actually returns you the old value. So you can look at that and1 and you know what it was there, that was value of 2. And so it's an update, but you can find out what was the previous value that you're actually updating. So that put method returns you that. Of course, if you try to remove something, well, then the entire entry will be gone from the map. Yeah. So you're removing the product 2, which is that T, which is this entry, right? And it will be just gone. Okay, what if we will try to check if something is or isn't in a map? Do we have the product P2 in that map? Contains key P2? Well, not anymore. We just removed it. So that has T variable will be false. The contains key method will return you false. You could also try to locate a value within a map. So contains value method, and you can look for something that has a value of, well, in this case, and1 is 2, right? And again, it's no longer present. That will be a value of 5 because we just updated it, right? Okay, and what about this example? What if we try to get something from the map, right? What do we actually get? If you say get me P1, which is that cake, you're not actually getting cake. No. You're getting the quantity for it, which is 5 in this case. Okay, that's how the hash map behaves, right? And it's a key value pair collection. Right, so next one, we're looking at the way in which we can iterate through collections. Several examples. The first example is Arraylist, and it's pretty straightforward. You added some content to it, and then you can just use it in a for each loop. It's as simple as that. You could use any collection in a for each loop because they all implement iterable interface. So it could be hash set, it could be Arraylist, whatever you want. DAC, yeah, you can just iterate. Now, you could use this technique. Out of the collection, you can get an iterator object, and the iterator object has a method called hasNext, which basically checks if the next element exists or not, and you can put it inside a while loop, for example, because it returns you Boolean, true or false. If next element exists, it returns you true. If it doesn't exist, returns you false. The method next allows you to retrieve next element, and you keep iterating. You can also remove values using the iterator. So there's a remove method. When it comes to the hash map, you've got a choice here. You may get a set of keys out of it and iterate through the set of keys, or you can get a collection of values and iterate for a collection of values. Or whichever way you want, really. So for example, the first example here gets the set of keys, and then for every key in the map, which is the map of products, using products as keys, you could get the actual quantity. Yeah, you could get whatever quantity was stored there. And the second example, you just get all the quantities and you ignore what keys are. Yeah. For example, if you want to compute something like a total, yeah, you don't really need the keys in this case. You can just get the values instead and iterate for a collection of values. So as you can see, the for each works nicely. And if you want to do a little bit more sort of advanced coding, then I guess you could use iterator instead of the for each loop. But that's how you iterate.